So this is our second intro lesson, building up enough skills to jump into the math, the calculations. So going back to rate laws and that generic formula, A amount of A chemical can react with B amount of B, making C amount of C, and D amount of D, where the little letters are all our stoichiometric coefficients. And then sort of reviewing and then expanding upon a rate law. So rate law has the rate equals a constant, and the other variables are concentrations. So we have two chemicals, two reactants in this generic example. We have chemical A and we have chemical B or reactant B. Okay? You're not going to see products in rate laws. Products are not going to be determining how fast something forms typically. Okay? Now the power of A, I'm putting in X. It is not little a. It might be, but it easily may not. The power of B is not little b, it is Y, which may or may not again be little b. So X and Y are experimentally determined. And again, and the value of figuring these out is you figured out something about the slow step of the reaction, and then you could postulate what the slow step might look like. Okay. Now another term to express X is referred to as the order of A. So A might be first order, it might be second order, it might be third order. First and second is the most common, first being by far the most common. If something is second order for A, it means two A's have to hit each other in the slow step. Okay? The probability of 10 things needing to hit each other at the same time and having orders of 5 for two chemicals is slim to none. So the probability of higher orders exponentially decays. Okay? Y is the order of B. And the sum of our orders is referred to as the overall order. And in advanced placement chemistry, we're going to do the math, the relationships with respect to time for only first and second order and touch on zero order a little bit. So an example kind of going the other way, you might be given a rate law. So I'm going to give you this. Rate is equal rate constant times the concentration of methane squared, concentration of oxygen gas to the fourth power. Okay. This is not necessary reality. This is just an example. So the order for methane, okay, you would not have to get confused by the balanced chemical equation. So CH4 times 2 methane mix 1 CO2 and 2 water. That does not tell us the orders. It's the rate law, and the order for methane is 2. The order of elemental oxygen is 4. And the overall order is the sum of the two, so that's going to be 6. Again, these are made up numbers. They are much larger than you would typically see. Last bit on this topic before we jump into collision reaction theory is what is the effect of changing concentration as a function of the order? So we're going to look at order 0, 1, 2, 3. We're going to look at what happens with a change in concentration. What does that do to the rate? And in all the cases, we're going to look at doubling in concentrations, what that does to our rate, what type of multiple is applied. So what happens if you 2x or double the concentration? Maybe it was 1 mole per liter and you double it to 4 moles per liter. What does it do if it's 0 order? Well, 0 order, I'm just going to stick in a Z for the sake of talking with a chemical. What if Z is doubled and it's 0 ordered? This would mean the rate is a constant times Z, and Z would be to the power of 0. So Z to the power of 0 is 1. So would doubling Z have an effect on the rate? No, Z isn't actually even a variable. So whether Z is doubled or half, it's going to have no effect. Okay? We could think of this as we have a doubling, but the doubling is being to the power of 0. So the rate is going to be 1x or 1 times. So if the rate was 10 before, doubling it, it's still going to be 10. You're going to multiply the rate by 1. It has no effect. Okay? The concentration is not a variable. It would not change the rate. If something is first order, and you double it, so the rate law is Z now to the power of 1. So if Z was 2 moles per liter, and now it's up to 4, that'd be an example of a doubling. Now that doubling, I'll leave the x out of the doubling. The doubling is to the power of 1. So this Z to the power of 1 term will be twice as big as it was before, so the rate will be twice as big. You've probably picked up the pattern. I'll go through the second and third order. So now we've got Z squared. So if you double the concentration, it doesn't matter the ratio, whether it's 1 to 2 or 2 to 4 or 1 millimole to 2 millimoles, the concentration factor will be doubled, but then we have to square that, and it's going to have a 4 times effect on the rate. So something second order, you double the concentration, it gets 4 times faster. Okay? There's a much bigger effect on the rate than there was on the concentration. And last, third order, I'm still doubling it, but if it's third order, we doubled it, but now it's cubed, the effect, okay, 2 times 2 times 2, which is not 6, there's an 8 times effect, okay, not 6. Sometimes students will do 2 plus 2 plus 2 instead of 2 times 2 times 2. Okay, so and 8 is almost 10 times. So if something is third order and you double the concentration, it almost has an order of magnitude or 10 times effect on the rate, where something that typically things are first order and then it's a nice linear relationship, double the concentration, double the rate if it was linear. Okay, So I'm only talking or writing out an example where something doubles in the order. If the concentration decreased in half and was third order, then the effect would be a half cubed, which is an eighth. So you don't have to do this just with doubling. Okay, if you 10 times the concentration and it was second order, the effect on the rate would be 10 squared. It'd have 100 times faster rate compare with that 10 times the concentration. Okay. So the order determines the power effect. Okay. So we have a couple key variables that are going to affect the rate of reaction. First of two I want to highlight is the number of collisions. Okay? This is why that concentration term has such a big effect on the rate of reaction. If you have a higher concentration, you're going to have more collisions per unit time. Higher chance they bump into each other. Where we might measure this is in, as I just said, concentration. Higher concentration, more collisions. Okay. And really pressure is the same thing. If the pressure is higher, okay, one of the likely reasons is there was more chemical put in and that drove up the pressure. It's not the only thing. Okay. Okay. The other factor is just because things collide doesn't mean they actually react. Okay. So what percentage of those collisions result in a reaction? Okay. This room was filled with nitrogen and oxygen, and they're colliding a unfathomable amount of times every second, but there's no reaction because they have a pretty much 0% reaction compared to collision count. Okay, so they're hitting each other, but they're not reacting. So you got these two factors. They got to hit, but just because they hit doesn't mean there's a reaction. Okay, a couple things to tie into that percentage of reaction based on a collision. There's going to be an orientation factor. So the molecules have to hit in the right orientation, and then they have to hit hard enough. They have to have enough energy to activate or start the reaction. Okay? If you're deficient in either one of these, you'll get a collision that doesn't react, doesn't involve a reaction. In this room with oxygen and nitrogen, the problem is the activation energy. They don't hit each other hard enough. Okay? The molecules are quite symmetric, so it's not that they hit each other wrong. Okay? An example or discussion on orientation is if carbon monoxide is reacting with oxygen gas, okay, which can make carbon dioxide and produce an unstable oxygen atom. Okay. Now doing some chemistry 20 bonding, if you did the structure, Lewis structure for carbon monoxide, you get a unique structure. There's a triple bond and carbon has a lone pair. And that's quite unusual for carbon. Diatomic oxygen is 2 O's. Let's see, what is the bonding capacity of oxygen? To remember our Chem 20. You'd start off by thinking of an oxygen atom that is in group 6A, so with 6 valence electrons, 2 pairs and 2 singles, and those 2 single atoms in oxygen means diatomic oxygen has a double bond. So this is going to turn into a bit more of an animation than a static note. If the diatomic oxygen hits the red O, after I group these, hits the red O, you're not going to get a reaction. Okay? Because in this reaction, when we produce CO2, which is a symmetric molecule with a double bonded oxygen on both sides. We need the extra O to come in on the left. So if the green oxygen hits here, it's just going to bounce right off each other and there's going to be no reaction. But if the collision happens on this side, then there is a probability of reaction. If it hits with enough energy, we could get this reaction forming. Okay? So this is a good example of a reaction where orientation would be important. The collision has to be the right way. Okay. The last factor I want to talk about on the bottom of this slide that can affect our rate of reaction, okay, which kind of can tie into both, but certainly would tie into the number of collisions, is temperature. Okay. Molecules that are moving faster are going to collide more often than molecules moving more slowly. Okay. Temperature relates to how much kinetic energy something has. If something is hotter, it's moving faster, it has more kinetic energy. If it's colder, it's going to have less thermal energy, okay? Less energy of motion. It's going to be going slower. Okay? That speed ties into our collisions. So I'm going to just talk for a second and then I'll pause and let you get the notes. This is a diagram with energy on the x-axis. So think of that as kinetic energy, which is coming from temperature. And we just have a count. Okay. Now let me draw something that's wrong first before you start writing. What you would probably think this would look like, if we look at energy versus count, you'd probably think that if a bunch of molecules are at 20 degrees Celsius, they would all have a certain amount of energy that would correspond to 20 degrees Celsius. Okay? And if you heated them up, okay, then they would all have more energy. Okay? All of them would jump to a higher energy count. Okay? But that's not what we get. Okay? Temperature is, or the energy at a given temperature is actually a distribution. This is our distribution. The middle of the hump is our energy average. Okay? And at 20 degrees Celsius, you might get a certain distribution. At 20 degrees Celsius, not every molecule has the same speed. Some have a little bit more than expected, some have a little bit less. And the average energy of the solution gives you a certain temperature. But it is an average of all the kinetic energies that causes a certain temperature. It's not that every molecule is going the exact same speed in this room. Some are a little faster, some are a little slower. So on this diagram is labeled activation energy. I'm going to highlight that in red. There's a certain energy needed for this reaction or a reaction to occur. So we have to have the right orientation, and then they have to have enough energy to start breaking bonds apart. Okay? That's the point of this diagram, is to get onto that concept. So at a certain temperature, we have a certain E average. I'm going to make up numbers. I think it helps the discussion. Let's say this is the profile for 20 degrees Celsius. Okay? Not every molecule has the exact same energy. Some have more, some have less. The middle would represent 20 degrees. Okay? This is our energy, our minimum energy to start breaking bonds, to start making new chemicals. So all the particles that have speeds or energies less than that red line are just going to bounce right off each other. Even if they hit in the right orientation, they're hitting too slow. Lack of energy. We have a small fraction where I have the red arrow. They're the molecules that are going unusually fast enough that they could cause a reaction. They also have to hit in the right orientation. If we warm this up, so I'm going to draw in, let's say it goes to 30 degrees. We're going to shift this average energy to higher energy if we're hotter. So now our distribution might look like that. Where the average has shifted much warmer. Now we have much more molecules that are going to cause collisions that have enough energy. I'll make my red line a little taller. And I'll do yellow. What's the area under the blue curve that have enough energy? It's all of those collisions now. A little more than half, it looks like visually, of the collisions now are going to cause a reaction at 30 degrees compared to what I drew for 20. Now the shape actually changes as it gets hotter. This distribution, as the temperature gets hotter and there's more kinetic energy, the distribution gets wider. Okay? There's an even bigger scattering of energies. The colder a solution gets, the narrower the peak gets, the less distribution you have of different potential energies. Okay? And this is sometimes referred to as a Maxwell-Boltzmann distribution. It's something in advanced placement you should be familiar with, a distribution of energies at temperatures. Hotter temperatures, higher energy distribution, fatter and shorter distribution. Okay? It's not a coincidence that I made that shorter. So wider. Okay. The total count or area under our curves are staying the same because we're not changing the number of particles. So we've got a lot of factors about reaction. Okay. The more collisions, the higher reaction. We have to have, there'll be a certain percentage of collisions that cause reactions. We've got orientation and temperature that can affect that. Last, which is just playing another visualization of activation energy, we're going to look at a chemical potential energy diagram. And we're going to build upon this in future lessons. And in regular Chem 30, we're going to be drawing these also. So this is purely a quick intro. This diagram shows potential energy. And in this intro, I'm going to do it versus time. We'll change that axis a little bit in the future. So what happens to the potential energy as a reaction proceeds? Okay. I want to talk about the combustion of combustion of methane with oxygen. There would be some amount of potential energy at the beginning. Nothing has happened yet, but there are 4 carbon-hydrogen bonds, and there's 2 oxygen-oxygen double bonds. So all those bonds have energy. Okay. I'm not putting a number to it, but I'm saying this line on our y-axis represents how much energy there is in all those bonds at the beginning. At the end, our products have less energy. The bonds in carbon dioxide and water. Okay. So the carbon dioxide has 2 carbon-oxygen double bonds, and our water, each water has 2 H to O bonds. So that's what I'm talking about when I say potential energy. Okay. Now I know this drops because I know energy is lost when this reaction occurs. How do I know? Because I feel heat and warmth, okay? And it's a cold day, and our furnaces are running and producing that heat that we feel. The chemicals have lost potential energy, okay? But methane and oxygen don't just collide and burst into flames every time they hit, okay? Every oil well isn't blowing up when a little bit of methane leaks out. There is a barrier for methane. There's a barrier for those to collide. The C's and H's don't just start breaking apart, and the O's just don't start breaking apart. There has to be enough energy to get them to come apart. That barrier we see as a up part of a chemical potential energy diagram. You have to put some energy in. Putting energy in raises the total potential. This is the energy that's going to start breaking things. Once you start breaking them apart, you break the CH bonds, the OO bond, then the new bonds are going to form. The CO2 starts to form, the H2O starts to form. Those new bonds release energy. Okay. But this up piece is energy that's required, and we call that activation energy. Even combustion reactions require activation energy. This would be the lighting a match, okay, to provide that energy to start a combustion reaction going. Once it gets going, the natural heat of the reaction will keep providing that activation energy, and will continue it. Okay. So that's our last concept, activation energy. So for practice for this section, again, this is from the Edvantage 2 workbook, and we're well set up in the next lesson to start determining rate laws. We're going to have instantaneous rates that we can then use and see what happens. When you double the concentration, what happens to the rate? If the concentration is doubled, and the rate of reaction doubled, then we know something's first order. But if we double the concentration and we get 8 times the rate of reaction, then we know it's third order. That's the type of math we're going to go through in our next lesson.